Oh, okay. Well, thanks to Aryan for giving the seminar today. The professor at ECE works on a lot of problems in optimization, reinforcement learning. So today's going to talk about meta learning. Excited to have you here. Thanks for giving the talk.
Thanks, Adam, for the introduction, and thanks everyone for joining the talk. So, as Adam mentioned, today I'm going to talk about adaptivity and its connection with representation learning and how it appears in meta learning and federated learning. Let's see if I can get it. Okay, that should do the job. All right, so before starting the talk, I just want to thank my collaborators. So this talk is based on two recent papers. The first one is on meta learning, ICML 2022, done by my student Liam Collins, our collaborator Sewoong Oh at UW, and my colleague Sanjay Shakkottai at UT Austin. And the second part of the talk is about a recent work on federated learning that is accepted for presentation at NeurIPS. It's again with Liam, my great friend and collaborator, Hassani at UPenn, and the usual suspect, Sanjay Shakkottai. All right, so let's just start a thought. So we're interested in the setting of multitask learning problem. So imagine you are given a bunch of tasks, and for each task, you have a few number of samples, right? And the important thing is these tasks are kind of similar to each other. They have some common structure. And the goal is to train a model such that when at this time I give you another task that you haven't seen, with a few samples and a few adaptation steps, your model is going to generalize well to that new unseen task. So that's the setup. All right. A good example of that is few-shot learning. Suppose at the training time, you have a bunch of tasks. The first task, for example, is distinguishing 3 different kinds of animals. The second one is 3 different kinds of animal. And for each of these tasks, you have a few samples. You want to train these tasks together such that at test time, when I give you another classification task between 3 animals that you haven't seen, you can still perform well with respect to that, given the fact that you have a few samples for that new unseen task at test. Okay, so you're going to get some samples at the test time before looking at the performance of your model. Again, it appears in other applications, so it may not be tasks, it might be changing environment. Suppose you're doing object detection using the camera of this drone in environment A, B, C, and you want to make sure that with some fine-tuning, the model that you have trained will perform well in a new environment D that you haven't seen. All right, so in summary, we're multitask learning. We have a bunch of tasks, few samples for each, and before deployment, I'm going to give you a few samples from the task that you're going to see at the test time, and you can somehow fine-tune your model with respect to that to measure your performance over the unseen task. Now, the question is, given this setup, what should I do at the training, right? How should I build my model? And after that, at the test time, when I have these few samples and a few computation, capacity, how should I fine-tune my model? After the yes.
So multitasking during training, you have
some
number of tasks.
Yeah.
Case you have some
single task.
single task, which is anyone of generalization.
Yes.
How do you quantify similarity? How do you quantify?
We'll see that. That's a very good question. So I'm just saying that they're not arbitrary. For example, in the example that I gave you, the first task was distinguishing cat from dog, and the second task was like, 2 other kinds of animals. So they're not completely different because you see there's some structure in the images of animals, but they're not the same, right? But there is some sort of similarity. Well, I'm going to quantify that.
The losses are the same.
The losses depend on the samples, but the loss functions are the same. All right, so now, this stopped working at some, okay. So now the question is how to train these tasks together. So a common thing, so let's formalize the setup just quickly. Suppose you have task 1 to task n, and suppose f1 is the loss function corresponding to task 1, which is defined by the mapping that you use and the loss function for task 1. And then you have all these tasks and all their corresponding loss functions. A common thing and the most natural thing to do is to say, hey, since I don't have enough samples per task, let's put together all these tasks, train a model that hopefully works well on all of them, and therefore it should generalize well because it works on a large number of tasks, right? So that's what people do, which I'm going to refer to that as average risk minimization. So I find a model that works well over all the tasks that you have at the training. Right? I'm going to refer to this as R. Again, this is the most reasonable, natural thing to do. And after solving this problem, I have a model, and then at test time, you give me a new sample, a new task, right? Another digit classification. But I have a few samples for this task. So what I can do, I can somehow fine-tune my model with respect to this task at the test time to get a model that better fits this new task, right? And you can fine-tune your model using one or a few steps of gradient descent. That's another very common technique that people use. You train, and then you fine-tune with some few steps of gradient or SG. And then after the fine-tuning, I'm going to look at the performance of your model. Okay, the setup is clear? All right. So this doesn't work. This doesn't work. Please.
So I'm still trying to understand. So let's say in standard training and finding, right? Let's say I'm training a mask language on some masking task, right? I want to fill in the blank. And we know that generalizes by to adaptivity, right? So if we consider n task instead of one good task, let's say like I'm training a language model with a mask, some code, right? So how is it different? Why is this better than training on one task?
So the point is you don't have enough samples to train each task separately, right? So if I had enough samples for each of these tasks or environment, I just solve each of them separately. There's no need, right?
I think he's asking about unsupervised.
Oh no,
throw away all papers and everything, just do one. So I think it's
yeah, but I'm the supervised learning set. Let's be that. Yeah. All right. So this doesn't work. In fact, in this very successful paper by Chelsea Finn, Peter Abil, and Sergey Levin, which led to the idea of MAML, they showed that if you just use this idea, which they call it pre-trained model, it doesn't work. So if you just minimize the average risk over all the tasks and then fine-tune, it performs relatively worse compared to their proposal, which we are going to go over it. So in both few-shot learning settings and robotics applications.
So when you say it doesn't work, it
doesn't generalize very well to the nuance.
with a few labeled examples
Yes.
of a new task.
Exactly. So yeah, this is, for example, the case that you only have one sample for the new task. This is for the case that you have 5 samples from the new task, like 5 should be. But in all these cases, the performance was not as good as they expected.
So that was their baseline that they beat with MAM.
Exactly. So far what I have told you that we have seen that if you minimize ARM using gradient descent or anything, and then fine tune it, it doesn't generalize well. So in this talk, I'm going to show that it's not just an empirical observation. In fact, in the case of multitask linear regression setting, we have a negative result showing that there's always a problem that this approach fails to learn the common structural representation of the solution, and as a result, it doesn't generalize well to new unseen tasks. And the positive result is saying that, hey, if you have some sort of adaptivity, either the adaptivity is in the objective function or in your algorithm that you're using, you can somehow learn the common structure or representation among the tasks that you're seeing at the training time, and as a result, your solution would generalize well to new unseen. All right? And this adaptivity idea can be encoded either in the loss function, which leads to MAML, or it can be encoded in your algorithm that you're using, which lead to the FedAvg idea and federated learning. It's kind of interesting that these two completely different topics, they have a very common structure that I'm going to discuss. All right. All right. So first part of the talk is about meta learning. So what is MAML? It's the same setup. The only difference between MAML and R is that instead of minimizing the loss, the classic average loss minimization, you're going to minimize the loss after one step of gradient adaptation. What's the logic? The logic was, hey, if I tell you at the training, you have these tasks, at the test time, I'm going to fine tune it with one step of gradient, then you shouldn't go with the classic approach, because I'm telling you in advance, I'm going to fine tune your solution. Then naturally, you would train for fine tuning. You would minimize the loss after one step of fine tuning.
So this fine tuning step uses the data of the new task.
No, it's during the training.
Okay, because I don't know that, right?
Exactly.
Okay.
So this is Fi and this is gradient of Fi. So for each task, I look at the loss function instead of Fi of theta, which is the loss of task I. I look at Fi of theta after one step of gradient with respect to that own function. So there's no cheating involved. I haven't seen the test data, right? It's all trained. It makes sense because I know that I'm gonna fine tune at the end, right? And that's the update of MAML. If you read the MAML paper, you may not see this formulation very clearly, but this is the heart of that idea, okay? So as an optimizer, when you see this, you're like, hey, this is just an initialization quick problem. I'm finding a good initialization that after one step of gradient, it would lead to good performance. And we during my postdoc, we looked at this problem with Asu and one of her students, Ali Reza. We looked at the optimization aspect of this and how the landscape of this problem changes and the optimization aspect of this problem. Because it's just like an initialization problem and it naturally moves your solution toward the harder task for gradient descent. Anyway, so that was our understanding. But I want to mention something before switching to the other perspective about MAML. So there is some sort of adaptivity involved in the update of MAML that the classic gradient descent does not have that update, that adaptivity. So suppose I'm just solving this problem using gradient descent, the classic average risk minimization problem. As you can see, all the gradients are evaluated at the same point, the current model, right? So there's no adaptivity with respect to each task whatsoever. But if I minimize the loss function of MAML, if you take the derivative, and if you know a little bit of algebra, you know that the derivative of this is giving you this I minus alpha Hessian times the gradient at this point, right? So ignore this preconditioner, ignore this matrix for a second. As you can see, the gradients for different tasks are not evaluated at the same point. They're evaluated at different points after one step of gradient adaptation. So this, even if you just run vanilla gradient descent on this loss function, you have some sort of adaptivity here. And a simple way to implement this is you just first compute these updates, and let's call it theta ti, which is the model after one step of adaptation. You plug it here in this formula, and then you get the new update, right? The new model, this is basically implementation of this update, right? But this is what people actually implement. What? Yeah, there was a question.
Suppose we are the over-parameterized world and there exists a common solution to all of the tasks. Then isn't the solution of gradient descent and MAML the same?
Not necessary. Not necessary.
I mean, suppose the common solution is theta star, then if you plug it in the MAML objective.
If you have one task, you're right. But if there is one, okay, if there is a solution that works for everyone, you're right. Right.
So if there is a set of parameters, right, that for all my existing tasks gives me, let's say, zero loss,
yeah,
interpolates, and I guess he's saying
because he's saying that I have a model that makes the gradient of each individual function zero. Right. So that makes the gradient of the.
So then you don't move. So then the MAML becomes, because
it becomes a vacuous problem.
Right,
it's like a single model. Yeah.
I'm missing something really basic. I mean, you're still evaluating everything on that math mode line at theta t.
Yes.
So,
but the gradients are evaluated at different points, right? If you ignore this term, right? This theta ti is theta after one step of local gradient adaptation, right?
oh, okay.
So these are not the same theta t.
Oh, I was looking up a lot.
So there is some sort of adaptivity hidden in this object. All right.
So let me understand that. So you wrote MAML in a way that I haven't seen before, right? And I don't know if other people, I don't know if that's a well understood thing, but certainly not well understood by me.
Yeah, that's what basically we did with Ali Reza. We just tried to understand what is MAML.
Yeah, I don't think even the first equation of your writing is something that's well known. Right?
Yeah.
So I just want to spend a little bit of time understanding.
Sure.
And then you say, okay, another way of doing MAML, which I guess is more commonly how people think about it, is they say, I have a model theta t, and I'm going to update for the, I'm just reading now your inner loop and outer loop.
So no, this is Alex. This is literally implementing this.
That's not obvious to me at all.
No, I'm just calling this
theta
ti, right? And replace this by theta ti here.
Yeah.
That's literally what I'm doing. Nothing fancy.
But I'm saying it's not trivial.
No, but this is they call it inner loop because this update can be done locally with respect to each task. You put them together and you do this outer. It's a fancy version of running gradients on this. That's it, guys. There's nothing fancy. We agree?
You have double.
Okay.
And that is the problem. Okay. Okay, so good. Just again, to take it easy. So the simple explanation that they give for MAML is they say, I'm going to learn a model so that after I update with one step for task one, I'm going to get some model theta T1, then I'm going to theta T2 with another one. And what am I minimizing at the end of the day?
So you're still minimizing this loss function. The average loss after one step of gradient.
They don't write that, right?
Yeah.
They never write that.
They
That formula is not written in the MAML. They write the bottom thing, right?
They only present this.
Right.
Without this, actually.
Right. So in order to actually do this, and that's where we're gonna go, you have a Hessian, right?
Yeah, but again, you need the Hessian. For a second, I'm just ignoring this precondition to make your life easy. But this is the true update of MAML.
Right,
this is what people do.
But that's not the MAML. The MAML paper said, maybe I would like to do this, and I can't do this, so I'm going to do a hack, and I'm going to throw away
They drop.
Right. So that's the first order MAML.
That's the first order MAML. FO MAML, as they call it.
Okay.
Yeah, fair enough.
So here n is number of.
N is the number of tasks.
Oh, okay, so it's
Yeah.
not like,
No.
okay, fine.
Within each task, you have a bunch of steps. All right, so yes, please.
But like, why is it so natural to do just one gradient step if you're going to?
Absolutely, you can do multiple, right? But I'm going to show one is enough. At least for the setting that I have, you can do multiple. You have to have in mind this becomes nasty.
Yeah, sure.
I mean, you can't even do one, right?
Yeah.
Even
this one is
you cannot
costly.
even do one correctly because there's a Hessian here. That's n. What's the dimensions? N by n.
It's D by D actually. And
Okay,
yes.
so model parameters by model parameters, right? So if I have a neural network that's a million parameters, it's a million by million matrix.
Yeah,
Like
and
100
times n.
terabytes.
Times n. You have to do it for every single.
So there's no chance in hell you're even going to write this matrix now.
All right. So again, as an optimization person, when I looked at this problem, hey, this is nothing except initialization. The rest is just here. And then this paper came out. This paper in 2020 came out, and they basically said, hey, we don't think MAML is an initialization problem. It's about rapid learning. It's about representation learning. And they checked this hypothesis by running this experiment. So they look at the model trained by MAML, right? And then they looked at the weights after fine-tuning. These are layers of neural network. These are how much, the y-axis shows how much the weights are changing, right? One means that the weights are not changing much. So they noticed that after fine-tuning, the first few layers of MAML, the model trained by MAML, after fine-tuning, they're not changing at all, or very little. But the last layer, which is the regression layer, it changes a lot. That suggests this idea that, hey, maybe MAML is learning the representation, and that's why it generalizes very well. Because the model is not, the first few layers of your model is not changing that much. So that should be, that we refer to that as representation, right?
But this is true for any function,
No,
not just multitasking.
no, actually, I'm going to show you that it's not true for ARM, for that, for if you do DGD, if you, like, we're going to exactly see this.
Actually.
They're gonna change, actually.
The other thing.
So then we looked at this paper, we're like, okay, can we formalize this phenomenon? Can we prove that MAML actually learns representation in some setting that we have to understand? Yes, sir.
So the learning rates here per layer. So it seems if we're interested about how much every layer
Yeah,
changes.
so like you look at the model,
Yeah.
right? And then you fine tune it,
Right.
given the task.
But you use a fixed learning rate for.
Yeah.
Okay.
Yeah, exactly. You just
So
see
you
how
could
much-
be,
yeah.
but your optimizer could be also, if this
No,
is.
no, like just want to see like, when you're fine tuning, really what layers are changing. That's basically what it is.
But I'm keeping my learning rate
You just do gradient descent with respect to
with a fixed learning.
expression.
But you see, if I'm doing this with Adam or something, I don't know what Adam is going to choose to do.
No, but Adam doesn't come up with layer specific steps.
Okay.
Multitask or simultaneous?
No, single task. You see a single task at training at the test time and you fine tune with respect.
You are end-to-end finding or head finding?
Oh, that's the whole point. They're fine tuning all the layers,
End-to-end finding.
but they can see that only the last layer is changing substantially.
Maybe this is just about multitask setup and gradients of multitask. So because you are trying to run a single task for not all the layers.
No, but that's the thing. If you have learned the right representation, it shouldn't change. But if you haven't learned, as we're going to see, all the layers are going to be perturbed much more than this. All right. So we said, hey, let's pick a single setup, a simple setup, and then prove this claim for that. So we picked this setting that each task is a linear regression. Suppose task I is a linear regression, the classic model. Theta I star is the ground truth model, the ground truth solution. Xi's are your feature vectors. They are Gaussian distribution, and Zi is your random noise, right? And Y is your label. So you have a few samples. This is basically the task of, this is how the data is generated for task I, okay? So again, if I want to solve this problem individually, how many samples do I need? If theta star is an RD, order these samples, okay? If I don't have samples, then what should I do? Now, more than that, I want to plant a common representation among these tasks. So suppose I have n of these tasks, right? And I'm going to assume that all these tasks, all these theta star share some sort of common structure. My assumption is going to be that all theta stars, they lie in a lower the subspace of dimension k, where k is much smaller than b. What does that mean? It means that there exists a b star in RDK, such that each theta star can be written as b star times w star I. Okay, so if you give me any of these theta stars that sit in RD, there is a mapping from RD to RK that you can say that theta star is b star times w star I. The important thing is there is no index I here, so the representation or the mapping is common. People also call this subspace learning, but I think of this as representation learning because my model for each task is a two-layer linear neural network. The first layer is B transpose, the second layer is WI transpose. And I'm assuming that the first layers are common for the ground truth model, okay? That's why I call it representation. So again, what's useful about learning B star? If I learn B star and you give me a new task, presumably I need to order K samples instead of order D samples because I've reduced the dimension of the problem. And so that's the value of learning the representation. There's only one assumption that you need task diversity, meaning that you need to make sure that if you look at the concatenation of WI stars, they span RK. Because you want to make sure that you have samples from all columns of B star, right? And this is a very, kind of like soft assumption, because if you think about it, the number of tasks is much larger than the dimension of the lower subspace. All right, so many of you, better than me, you know how to solve this problem. You can do PCA. There are many things, there are many techniques to solve this problem. I'm not in the business of solving this problem in the most efficient way. I'm coming up with a setup, and I'm saying that, hey, if I run GD on ARM, do I learn B star? If I run GD on MAML, do I learn B star? That's my question. Does GD on ARM learn the common representation? Does GD on MAML learn the common representation? These are the two fundamental questions that we want to answer. All right, all clear?
So if you don't have the task diversity condition,
Yes.
there's infinitely many solutions. That's a problem.
No, all I need, like suppose that I have all WI stars are like parallel, right? Then I can only see the energy of B star toward one direction, but I need to see all the energy of the columns.
So there are infinitely many solutions. That's what I'm
Yeah,
saying.
exactly. And not like you don't necessarily see all the columns of B star, so there's no way to recover B star, right?
There is no way.
There's no way to recover. All right.
How does this relate to the setup that Simon wrote at?
It's very simple. It's exactly, the setup is almost identical to the setup that they have. They are not in the business of how to solve this problem. They just say, hey, if I learn B star, what would be the statistical performance that I would get?
So which paper Simon do the by MAML or?
No, there is this, this model was first proposed by a paper of Simon Du and Sanjay Shakkottai, I think. And then Chi-Jin and Michael Jordan, they also look at the, sort of like a generalization performance of this model. And then they looked at the nonlinear version of that. But we're just using their model as a model that has some sort of like common representation. And we're trying to see that if I minimize the average risk, what would happen? If you minimize the objective of MAML, what would happen? All right, yes.
This type of sharing certain latent factor is very, very common for any task in multi-task.
Yeah.
That's usually way before meta.
That's true. No, but he was referring to that. It's not about meta learning. It's actually, again, this setup has nothing to do with meta learning, right? I'm just using this as a setup that I know there's a planted representation. And I'm trying to see if I follow meta learning, can I learn that? And if I follow just average minimization with gradient descent, would I learn it or not? We know how to solve this problem. I'm investigating these two approaches that I discussed. So in this case, the loss function becomes this. It's, your model is B times W, and this is the loss of task I, and then the average risk minimization, you just minimize the average risk over all the tasks, and you learn one B and one W in each case. You learn one theta, which is B and W, when you run the update of MAML, so you have this inner loop that I discussed, right? You update W and B's with respect to the local gradients, and then you put them together, the Hessian term, and you get the new model. There's one thing I want to mention. If you only adapt the head, which is W, and you don't adapt B, there's this other algorithm called anneal, almost no inner loop algorithm. So the only difference between that and MAML is that in the local adaptation step, it's like a kind of like a hack, because no formulation actually, like the formulation that I told you about MAML doesn't lead to that. But they're saying that, hey, let's just adapt W and don't adapt B in the local. And I'm going to analyze both of them in this talk, okay? We just want to make sure that you see the difference between MAML and anneal. Yes.
So anneal is just a specific version of MAML where the specification for fine tuning is restricted to the last layer.
Yes, yes, but you still have adaptation here in the outer loop, right? But when you're doing the local adaptation, you only locally adapt the head, not the verb. So yes.
Okay, so each task has a different prediction. Anneal is updating only the prediction.
No.
And
No.
MAML is adapting the entire attack.
So now my point is like think of B and W as your theta, right?
Yeah.
MAML does one step up gradient with respect to whole theta.
Right.
Anneal says do one step up gradient only with respect to W, not with respect
within the
to
prediction.
X. That's what, yeah.
But there could be a version like Anneal Light, where you, if I'm understanding correctly, which I'm probably not, where you have BT everywhere. Isn't that?
Yeah, that's true. Like all the BTIs are exactly BT. That's exactly what anneal does, right?
Oh,
So it doesn't
so
locally.
it's already done. Okay.
All right. So before proving everything, we run some experiments to see actually if it works, if the hypothesis is correct. And surprise, surprise, yeah, it's correct. Or if you run gradient descent on average risk minimization, you don't learn the ground truth representation. The distance between BT and B star is not getting closer. But for all these meta learning algorithms, MAML, anneal, first order MAML, first order anneal, you exponentially fast learn the ground truth representation. All right, sounds good. Can we prove it? The answer is yes. This is the informal version of the theorem. So we say that under standard assumptions, MAML and anneal on the first order versions, they're exponentially fast learning the ground truth representation. In terms of sample complexity, the number of samples that you need per task, instead of being order D in the single training case, it's D over N times K cubed. We would love to have K here because the number of parameters that you're learning is D times K. But the analysis was not tight, so we got K cubed.
K is the number of tasks.
K is the lower dimension. Is the size of B. B is D by K.
So the assumption is that there is a K dimension. K is the dimension of the representation.
The lower dimension. Yes. B is representation is D by K, right? It
Right.
maps you to the lower subscript that dimension.
So it's the hidden lower dimensional representation. Okay.
The dimension. So K is much smaller than B,
Yeah.
right? And if you have more tasks at the training time, then you can argue that D times K cube over N is much smaller than B, and multitask learning actually helps, meaning that you need less samples per task to learn the ground truth representation. All right, so what's the key idea? Why does MAML learn the ground truth representation? And at least numerically, we saw that gradient on ARM doesn't learn. The idea is the adaptivity step in MAML allows us to leverage the task diversity and learn the ground truth representation. And this is something that I'm going to build on in the upcoming slides. But I have a negative result in a very informal way. I'm saying that there always exists a problem for which, if you run GD on R, average risk minimization, you won't be able to learn the ground truth, the right column space. I'm going to formalize this, but this is the positive result. This is a negative result. ARM doesn't work, at least in some cases, and MAML always in the multitask linear regression set. All right, so
in ARM, are there many? Is there a W per task, or is there one W per?
is log 1 W.
Yeah.
By the way, in MAML, you're also learning one theta. At the end of the day, MAML, you're learning one theta.
Yeah.
There's no cheating involved. I'm not saying that, hey, learn one B and multiple W.
What is that? What's W? W is
W is the head.
W is the head.
So that's the important thing.
I'm learning one model. Like both models.
Yes,
There is one
exactly.
model. Yeah.
So that's actually a very important point. You have to have in mind, if I change my optimization problem in a way that I'm forcing one B and multiple W's, yes, you would expect that. The surprising part is MAML is only learning one B and one W. Yes, the updates lead to some adaptation, but the output is one model, one theta, one B, one W.
Yeah, but that's kind of a weird setting, right? Because if I have a 10 label problem, let's see for 10, and I have another 10 label problem like M this, you're literally using the same head for both, right?
Yeah.
So it's kind of a contrived setting.
But you can think of the case that, you just pad zero for, you go with the larger one and then you pad zero for some of the W's of the task that they have.
That's not how it's said, right? Like
Yeah.
that, yeah.
Yeah.
Yeah, so it's a contrived setting.
Yeah, but I'm
Like,
assuming that.
all 10 label problems are not the same. Why would you ever use the same head?
I agree. But the important thing is the map, like, I mean, the way that I think about it is that I have to put some assumption on D, right? And when I'm assuming that B is exactly the same for everyone, it's from D to K, I'm forcing you to go with, the W's that are in the same dimension.
So I guess the problem, is there a problem, an open problem that Sujay is pointing at here? Because he's if I'm understanding you, his setup, which I think is, you're saying the correct thing. And
so
is there an open problem that I allow the last layer for it? So when I'm doing this average discrimination, I could allow, and that's what we practically do. I would allow the head per task to be different.
Yeah.
So I would have K times the extra. You see what I'm saying? I would have K times the extra.
if I like my analysis 10 times easier if I was doing it.
No,
And I would, let me explain.
Yeah. Let's talk about
The
it.
challenge is, how can I ensure if I minimize the loss of MAML, which learns only one B, and one W,
Yeah.
is still it's learning the representation. The W could be garbage. I don't care about it. I want to learn the representation.
Right.
If I fit B to be the same and W's are different, I'm sort of like helping the algorithm because they're separate, like you're pushing the W's to give you different columns of B, and then it makes the problem much easier.
What I think
So the baseline algorithm idea of using the same W for the task just doesn't make any sense.
No, that's what people do. Like they literally minimize just one, like they train single, like in multitask learning, you don't, like, how do I know how to go out with different W's? I don't know, where should I cut it to common? Where should I cut it to personalized? Right? You just train a single and then you fine tune with respect to head if you wish. Right? I don't think they force it in the optimization problem that they have, at least in the, the benchmark that they use in the MAML. We can discuss it. Yeah.
let's discuss on that.
I mean, if there are people who can figure out what's the common representation, what's the personalized, it does make sense to decompose your solution in that way. But if you don't know, right, you just train a single model. And MAML says that, hey, I'm going to train a single model and I still learn. Yes.
So, did you also check with like applying some kind of regularization concept?
Yes. So if you do regularization, orthonormalization, all these tricks, your life is much easier. The analysis is much easier. But I want it to be honest and exactly follow the dynamic of MAML. And that would make the life much easier if you have regularization, because regularization is putting an assumption that I know that, this is the head, this is the representation, and so on. Right?
No, I mean like for R, like you apply on R, with R, you apply to regularization on B. So will that also not learn B properly?
I haven't done the analysis, but I think it might help. Yes. Yes. Because it would, it might, especially if you have a W regularization.
So what if we just learn the B's, right? So let's say I have n tasks, right? And
So I think his point is not, he doesn't want to learn the B, he wants to use the framework to understand.
Exactly. It's just a setup. I want to see in this setup that you have a common representation of what would happen for R, what would happen for MAP. That's all, right? All right. So I have only 10 minutes, and I'm on slide 16.
you can take 15.
Thank you, but I have 40 slides. But also, we can consider this as a service to the department for teaching meta learning and MAML. But yeah, let's get to the result. So the catch here is, if you do R, right? If you do gradient descent with respect to R, what's going to happen if you look at the infinite sample case? For the simplicity of the presentation, I'm going to assume that the number of samples per test is infinite. And look at the dynamic of gradient descent. What you're going to see, the new BT that you're going to get is a combination of BT and B star. The important thing is this object is a rank 1 matrix. That means that I'm killing energy of B in only one direction, right? And if you look at this object, it's also a rank 1 matrix. That means that I'm learning only one column, like B star towards one direction. And due to this problem, you may not be able to kill all the bad energy and add all the good energy in a nutshell. And because of that, you may not be able to learn the ground truth representation. Using this observation, we could come up with this negative result. saying that suppose you have an initial matrix B0, whose principal angle distance with respect to B star is some delta, right? So basically pick a B0, pick a step size, pick a number of iterations, and pick any WI stars that you want. I will give you a B star whose principal angle distance to B0 is small. It's delta between 0 and 0.5, right? And after that T iterations, the principal angle distance between your output of arm and B star won't be smaller than 0.7 delta. So even if the initial B0 is close to B star, something between 0.0 and like, because you would like to send this to 0, right? I can always find some B star that even after any T iterations, you cannot get closer to 0.7 of that. That's a negative result. So there's always a bad B star that I can cook up.
Sorry, so see, in the dynamics that you wrote, like, what if I added, N2 regularization of B? Won't it like have a similar effect on making you don't want to make it?
No, not necessarily.
Just explain this. No, I mean, no. While I'm comparing R, because part of the paper says that, ARM does not work, right? But ARM bit L2 should have a similar effect.
I'm not sure if this time is going to be full rank. You might be able to make this full rank, but not the other.
Something similar, right? You would have P times I minus 1 minus B.
I don't think it's going to be. Yeah, we can check it. I don't, at top of my head, I don't know if it's going to, both of them are going to be full rank. All right, the important thing, if you do the update of gradient descent on MAML, what you're going to have here is the transpose of WTIs, which are your heads after adaptation. And if I can manage somehow to show that WTIs are diverse, then this matrix is going to be full rank in RK. And as a result, I'm killing all the bad energy of PT in all directions. And if I can show that WTIs are sort of aligned with WI star, since WI stars are diverse, this is another full rank matrix, and I'm adding all the good energy in all directions. So in fact, you can get an exponentially fast convergence rate in this case. And that's the reason that we get a linear convergence rate, because you have a contraction here and you're increasing also exponentially fast here. So now the only thing that I have to answer is that, can I guarantee that WTIs are diverse and they span RK, right? So, and to do that, I just look at the update of WTI. The update of WTI, which is one step of adaptation with respect to Fi, it can be written as this. And if I want to make sure that WTIs are diverse and they're close parallel sort of to WI star, I need to make sure that this term is small, this term is small, and this term is large enough. Meaning that I need to make sure that BTs are diverse and WT has a small norm and BT has enough energy towards B star. But the problem is you cannot easily guarantee all these three conditions hold for all the time from 0 to T. In fact, you need 6 different things to hold from time 0 to time T in order to make sure that everything works and you get the linear rate and all these conditions that I want here, they will hold. So you need to make sure that norm of WT stays small, the B's are getting closer to orthogonal, are becoming orthogonal, and the BT stays uniformly close to orthogonal normalization, like meaning that BTB transpose is close to identity, WTIs are diverse, and these 2 other conditions are like the linear rate and the overall linear rate. So you need all these 6 hypotheses to hold from time 0 to time T. And they're interrelated to each other. Like one, in order to make sure that one holds at time T plus 1, you need a few things to hold at time T and a few things to hold at time T plus 1. I'm not going to go over the details. I'm running short on time. So it's a nasty multi-step induction argument that if you do, then you can get to the dreamland and you get the linear. All right. So for all these algorithms, MAML, annual F1, annual F1 MAML, you can get a linear convergence rate to the ground truth representation. And the conditions are slightly different. The initial conditions are slightly different, but the linear rate is relatively similar. I'm not going to go into the details. Again, if you want to check the difference between the initial conditions, I would be happy to chat offline. This is for infinite sample case. The similar results for finite, like yes.
If you don't want the linear rate, is there a simple argument?
I wasn't chasing linear rate. It was just naturally coming from the, yeah. All right, so I want to finish the first part of the talk by saying that basically how I convince you, if you don't have some sort of adaptivity in your updates, you won't be able to leverage the task diversity and learn the common representation. What MAML does, it sort of like encodes this adaptivity into the loss function via this gradient of adaptation that you have. But this adaptivity could come from the algorithm that you're using for your problem, which is closely related to what we do in federated learning. So let me recap what ARM does very quickly. So in ARM, you just minimize the average risk minimization, you find a model, and then you fine tune it with respect to the task, the new task that you're going to see. What if, so imagine the case that these tasks are, and their corresponding data are at different computing units, right? Suppose the task 1 is at computing unit 1 and task n is at computing unit n, right? And they don't want to share the data. There's a server, you can just communicate your models with that server, which is the distributed learning setting. Now, how would you solve the average risk minimization problem? You would ask the server to send down the model, and each user or each client would run one step of local gradient with respect to their local loss function. They find a new model, they send it up, and then the server computes the average, right? If you put together this update, this is nothing other than running gradient descent with respect to the average risk minimization. So what we're doing, we're basically implementing GD on ARM in a distributed manner. So nothing fancy, and it should work in the sense that it follows the same dynamic, but we know from the previous part of the talk that it won't learn the representation, at least in the multitasking regression setting. And this is called distributed SGD. Then, completely irrelevant to representation learning, people came up with the idea of federated learning. What's the idea of federated learning? Instead of running DGD, for each iteration, you need one round of communication between server and the client. Why not just send down the model, run a few local updates, and then average the model, right? So it was initially done because of the fact that they wanted to reduce the communication costs. And it makes sense because, once in a while you have to communicate with the server. And suppose I'm going to call tau as the number of local gradient updates that you run before sending your model to the server. So the advantage is you reduce the communication costs, but the disadvantage is you're drifting towards the local solution of each client, right? So if I run, it's a very obvious thing that you can see that if I run 2 local gradient updates and look at the average, it's not equivalent to running 2 gradient with respect to the global objective function. In the extreme case, if I solve each of these problems exactly, the average of minimizers is not the minimizer of the average, right? So you have this drifting issue that is happening, especially in the data heterogeneous setting, because these gradients are not aligned with each other, right? So from an optimization point of view, FedAvg is a very bad thing to do because you're drifting from the ground truth gradient direction, right? And there are tons of works in federated learning for addressing this issue. This was well studied in these 2 papers showing that you have to use a diminishing step size to control the drifting effect. Many people came on, including myself, we came up with some fancier versions of FedAvg with gradient tracking to sort of like make sure that locally when you're running gradient, you're still tracking the global gradient directions. Again, these are all coming from an optimization point of view because I want to stay close to the gradient of the global objective function. But when we ran some experiments to see what happens in terms of generalization. If I want to compare the model of FedAvg with the model of DGD, how would they compare with each other? So in the left plot, I'm looking at the models trained on 80 classes of CFAR 100, and I'm testing them after fine-tuning on 20 new classes of CFAR 100. So 80 classes at the training time, 20 classes at the test time, and I'm comparing the performance of FedAvg with DGD. Yes.
Yeah, just want to check this on this answer. You didn't talk about the generalization without the first part, right?
I did, because when you learn B star, that's all you need. If I learn B star, my solution would. Yes, absolutely, absolutely. Yeah, if the new unseen task has that common representation, yes. If not, yes, absolutely. So now, as you can see, the model trained by FedAvg generalizes much better to new classes of CFAR 100 compared to the model trained by DGD, right? And I'm not cheating, the number of overall gradient computations are the same. For example, if tau is 50 and the number of communication rounds for FedAvg is 2,500, I run DGD for 125,000 iterations, so that the total number of gradient computations are the same. In this case, I even changed the data set. So they're trained on CFAR 100 and they're fine-tuned with respect to CFAR 10 at the test. Still, you see that FedAvg generalizes much better than DGD. That doesn't make any sense because FedAvg is not even minimizing the right loss function, quote unquote, but it generalizes better. Then we looked at this idea that maybe FedAvg learns the common representation and DGD doesn't. We ran the same test. And as you can see, the first few layers of FedAvg, they change much less than the first few layers of DGD after fine-tuning. So we said, hey, maybe the same phenomenon is happening here. Can we formally prove this? And can we formally show that these local updates are actually helping to learn the common representation?
Sorry, what do you mean by the pre-trained model? It's not a federal learning construct.
So no, this is the model. We are looking at the model trained by FedAvg after fine-tuning. And then we are saying, we are looking at how much its weights are changing after fine-tuning. Yes, yes. All right, so we use the same model, same assumption. Again, for the same reason, R, like DGD shouldn't work because it's just literally GD on R. And we know that. Interestingly, if you look at the update for the average, it's much more, it's way messier than the update of MAML because of these tau local updates that you have, and you have this product of these matrices. But if you simplify it, you get this nice structure. That is still, you see the same behavior is happening here. You have these full rank matrices, and in fact, if tau is larger, up to some point, it's helping your convergence rate, and this matrix becomes better conditioned. As a result, you have a faster linear rate. So I'm not going to go over the details because we're already running out of time, but you get the linear rate, and the important observation is that up to some threshold, if you increase the number of local updates, you're actually improving the process of learning representation, and after some point, it doesn't matter. So if tau is something between 2 all the way to 1 over alpha squared, it's helping to run more local updates, and after that, it doesn't matter. I mean, you get the same performance that you would get for 1 over alpha squared. But alpha is the step size that you're using. And I think this is one of the first results showing that FedAvg is capable of representation learning.
So so what you do exactly algorithm? So each client has one task.
Yes.
Data for one task. You train it independently.
No. What I do, I run a few local updates.
Local updates,
And then the average.
head, like linear head, right?
So basically what I do is like I have this B and W. I receive it from server. I run multiple steps of gradient with respect to both of them locally. Then I send both of them up, and then I compute the average. That's going to be the new model.
Okay, so
That's for the average.
So for all the clients, you send PI and WI for each
Yes.
client, and then you average them.
Yes.
Okay.
Because that's my theta, right? That's my home model.
But how about just like if you throw away the WI, right? Because at server, we are learning a new one, right?
Yeah, you can do that.
Has people done that or case?
I mean, that was actually our previous paper. We were saying that just exchange B, but that for that case, we have to assume that the clients are learning different heads. But since I'm just running FedAvg, in FedAvg, that's not what people do. FedAvg, you just simply look at the average of the whole
But
model.
you are running local history, right? With local data.
It's local SGD.
But like, let's say client type, it has task type, right?
Right.
So it has different data than client J.
Right.
Right, so the WI will be different than WJ.
Right. They will.
For the
Even B's are going to be different.
I don't,
Yeah.
So intuitively, what makes sense is like, I mean, intuitively, first idea that comes to mind is like you just share BIs, average them out, attach a W, and learn whatever. Let's say.
So that's a very good point. I'll get back to that. In fact, you might say that, hey, if I solve each of my local problems separately, and then I look at the average of B's, that would have the right representation. The answer is no.
And learn W.
No. Let's look at it. So suppose if I solve each of the problems separately, right? Then BI times WI is equal to B star WI star, right? So if I put together W's, the columns of W, it has the right column space, but the average doesn't necessarily have it, right? For example, suppose your B1 that you're learning is E1 and 0. Your B2 is E2 and 0. So if I put together, it has the right column space, which is E1 and E2. But if I look at the average, it's 1, 1, zeros, and zeros. So the average does not necessarily maintain the whole column space. And that's the whole reason that we had the same perspective. We said, hey, I locally run many updates, I should be fine. But when you do average, you cannot guarantee that you preserve the column space. And that's why we had to move to the classic proof that we had for MAML, going through the inductive argument and suffering for a few months to get the induction work, right? Yes,
Hi, on stage, I didn't see you found that the low end success.
I do. No, I do. I do. I basically said it's the same model.
Oh, okay, here. So, and by the way, just a comment and inspired of the previous question. There was a new paper by Aryan Mokhtari and Ludwig called the low five distributed fine-tuning. And they basically say what he just mentioned can work if you are doing fine-tuning on pre-trained for the knowledge from scratch, which is not very scientific.
That's absolutely right. So again, it's going back to the fundamental question that I want to answer.
Well, we're fine-tuning
So Atlas,
by the way, we cannot make it work on all of them. So things come to use it for very long time.
so again, the question that I'm hearing trying to address is not how to learn V-star. The question is why does FedAvg generalize better than DGD? And that's a very weird thing. DGD, from optimization point of view, which I'm showing you this slide, my final slide, Adam, I'm sorry. So if you look at the gradient norm of the global objective function, DGD is exactly doing what you want. And it's getting to a first illustration point. And FedAvg with fixed step size, it fails to get even to a first illustration point of the average risk minimization problem. From optimization point of view, it should be complete garbage. But from a representation learning point of view, that local updates that you're running, it gives you the adaptivity and it leverages the task diversity and it learns exponentially fast the representation. And for that reason, it generalizes better to new domains. So all I'm trying to say is that when we're doing federated learning, it makes sense that we are, as an optimizer, I'm guilty of the same thing. We all just care about, hey, how can I solve this problem, get to a station point of that? But maybe that's not all we have to think about. We should think about the generalization aspect of the solution that we learn. And that's something that is explained. Yeah.
Alex, let's finish up. We can take questions.
Yeah. All right, that was it. Thank you so much.
All right, thanks, Aryan. Take questions offline because we're
Up to you. Yeah.
thank you.
Thank you, everyone.